The brain's sensitivity to insulin signaling has emerged as a critical factor in cognitive health, with growing evidence that peripheral metabolic dysfunction impairs central nervous system insulin action. Understanding these mechanisms clarifies how dietary patterns affecting whole body metabolism ultimately compromise memory and cognition. Insulin in the brain serves functions beyond glucose regulation. Neuronal insulin receptors modulate synaptic plasticity, the cellular basis of learning and memory formation. When neurons respond appropriately to insulin, they strengthen connections efficiently during new learning. Additionally, insulin signaling influences neurotransmitter release, particularly affecting acetylcholine systems crucial for memory encoding. Peripheral insulin resistance, the hallmark of type 2 diabetes, doesn't remain isolated to muscle and fat tissue. Research using specialized imaging techniques reveals that individuals with metabolic syndrome show impaired insulin transport across the blood-brain barrier. Cerebrospinal fluid analysis detects reduced insulin concentrations in the central nervous system despite elevated peripheral levels, indicating transport dysfunction. The cognitive consequences prove substantial. Longitudinal studies tracking individuals from middle age through late life demonstrate that those developing insulin resistance experience accelerated cognitive decline, particularly affecting memory and executive function domains. Effect sizes suggest that insulin resistance may account for 10 to 15% of dementia risk, though estimates vary across populations. Mechanistically, impaired brain insulin signaling disrupts multiple processes essential for neuronal health. Reduced insulin action impairs synaptic glucose uptake, potentially starving neurons of fuel during high metabolic demands. Additionally, insulin normally promotes the clearance of amyloid beta protein. When signaling falters, these toxic proteins accumulate more rapidly, potentially accelerating Alzheimer's pathology. Neuroinflammation represents another pathway. Insulin resistance associates with elevated inflammatory markers systemically, and emerging evidence suggests these inflammatory signals reach and affect brain tissue. Chronic neuroinflammation interferes with normal synaptic function and may accelerate neurodegeneration. Animal studies provide causal evidence that human observational research cannot. Mice genetically engineered to have brain-specific insulin resistance develop memory deficits without peripheral metabolic problems, demonstrating that central insulin action matters independently. Conversely, restoring brain insulin sensitivity through various interventions rescues some cognitive deficits. Human intervention studies remain limited but promising. Small trials testing intranasal insulin, which delivers insulin directly to the brain while bypassing systemic circulation, show modest memory improvements in people with early cognitive decline. While not yet ready for clinical application, these findings support the principle that brain insulin matters for cognition. The dietary implications center on metabolic health preservation. While the specific impact of sugar per se versus overall caloric excess and body fat accumulation remains debated, chronic high sugar intake clearly contributes to insulin resistance development. Reducing sugar consumption represents one component of dietary strategies preserving insulin sensitivity. Physical activity proves particularly effective for maintaining insulin sensitivity, including in the brain. Exercise increases insulin receptor expression and signaling efficiency. Combined dietary and exercise interventions show superior metabolic outcomes compared to either alone. For individuals concerned about cognitive longevity, the research suggests prioritizing metabolic health decades before cognitive symptoms typically emerge. Insulin resistance develops gradually, with brain insulin signaling likely affected years before clinical diabetes diagnosis. Preventive strategies initiated in midlife or earlier potentially prevent or delay cognitive decline. The neuroendocrinology remains incompletely understood. Questions persist about whether all insulin resistance patterns equally affect the brain or whether specific metabolic phenotypes pose particular cognitive risks. Additionally, genetic factors influence individual susceptibility to insulin resistance and its cognitive consequences. Nevertheless, the accumulating evidence establishes brain insulin resistance as a meaningful mechanism connecting metabolic health to cognitive aging. The practical message proves straightforward: dietary and lifestyle patterns preserving whole-body insulin sensitivity likely protect brain function simultaneously, offering a concrete link between nutrition and cognitive preservation across the lifespan.